Yeah, thanks for Zhigang for organizing this. And it's great to have so many familiar faces and also excited with the unfamiliar faces. So it's a pleasure for me to be back here, and I'll talk about the probability of the cut locus of a Fréchet mean. This is joint work with Alexander Luchak, a geometer from Karlsruhe Institute of Technology. Wilder, his colleague of.
It's a different institute, Stephan, but
is it?
It's not algebra and technology, it's algebra and geometry.
Oh, okay, sorry. Thank you. Yes. So please interrupt whenever.
It would be nice.
Yeah. Sorry?
Yeah, happy with everything.
So please interrupt me if there's anything not correct. So I'll give a motivation why the cut locus is why it's interesting to look at this. Then afterwards, precise definitions, previous work, and main results. Then we'll do some first order considerations to understand what's going on. Then this leads us to a digression to stickiness, so how that relates to stickiness. Then we'll do some second order considerations and finally get the result. And hopefully there's time for discussion. I should say Alexander has done all the first order and second order considerations. So the meat of all this is due to Alexander. Okay, so our setup for this entire talk, except when we go into stickiness, is a complete and connected Riemanian m-dimensional manifold with an inner product, which gives rise to a geodesic metric. And of course, statistics with random variables, IID on our manifold, and they give rise to Fréchet functions. So for all people who've not seen this, so here's a test point on the manifold, the distance to a random object. So this is a random squared is a non-negative number. We can take the expected value, and that is the Fréchet function. And the sample function is just the same, only summing over the sample, and will require until almost the end of the talk, always that this second moment exists at least for one point, then exists for all points. And of course, minimizers of those Fréchet functions are the so-called Fréchet means, population-wise and sample mean, and they might be set valued. And this is essentially what Fréchet introduced in 1948 for metric spaces. Okay, and of course, this is a generalization of the Euclidean mean, because if you plug in the Euclidean distance, minimizer will then be just the expected value and the classical mean. Okay, and since statisticians are interested in testing and all sorts of similar things, so they want to have central limit theorems. Asymptotic, these are the non-parametric statisticians who do the asymptotics. Of course, there are also finite sample results, but so here we do asymptotics, and we're interested in the case we have a unique mean for the sample means. We assume a measurable selection, so it could be non-unique. There's the well-known result, I guess, dating back to Zietzold, again on metric spaces. In very general conditions, we have that the sample means almost surely converge to the population mean. This has been refined by Vic Patagennaro and Robbie Patagennaro in 2003. But we want to have a central limit theorem, so we need a little more. We need something twice differentiable. So we assume there's locally a chart near the mean, near the unique mean, such that this distance function, so here's a chart, we're mapping back from the chart to the manifold. This should be almost surely twice differentiable. So recall that X is locally, is refined is restricted to chart, but the capital X's, the random variables, can be anywhere on the manifold. And then we need, of course, some, so we take the derivatives, here the gradient, we assume this exists, they take the covariance at the mean. We want to have the, yes?
The if is supposed to be inside number one, right? So if number one, then number two? Or if also there exists.
No, if is everything. If 1, 2, 3, 4, and this is just a side remark. Yes.
Very good.
Okay. Thank you for this is exactly what I need, whether it be technology or geometry or thank you. And actually, this is due to I inserted this later. I had this down here as a result.
No,
I think
it's all good. Just making sure I understand.
yes. Thank you. Okay, we also want, now this is a little more complicated. We also want to have a second derivative of this Fréchet function to exist at the mean. And here is something which will be clear once we go to the proof. We want to have random sequences converging to the image of the Fréchet mean. So we're in the Euclidean space here. So for every random sequence, this empirical process, the Fn, so this is the sample Fréchet function, should converge almost surely to the Hessian. Yes, and we want to have this, oops, here we go. Then eventually you get the central limit theorem by Vik Bhattacharya and Ravi Bhattacharya, which tells us pretty much what you expect. So these are vectors in a Euclidean space, rescaling with the square root of n. This converges to a Gaussian. Here is the covariance. You would expect that guy. And here are the Hessians, of which we require to be invertible. And the proof actually goes through, is very simple, straightforward. It's kind of hid in the original publication because they were struggling with all these conditions, I guess, but I guess it boils down to the following. So we assume without loss of generality that with our local chart, we are actually, the mean sits at the origin, and then the sample means are also points close by. We know they converge almost surely. And so we can write down the Fréchet function here at the, I guess I should probably even have, maybe I don't. Yes, there's. So we take the Fréchet function at the sample mean, and we assume this exists almost surely, is twice differentiable. So it's a minimizer. This guy is a minimizer of the sample Fréchet function. So taking the gradient, that should vanish almost surely. Next is just do a Taylor expansion of this Fréchet function, so at the origin. And the next derivative, the Hessian, that's how the Hessian comes in. And here we see a random sequence because these guys live between the xn, the images of the sample mean, and the population mean by the mean value theorem. So, and this whole thing boils down to, well, these Fréchet, the sample of Fréchet function is just a sum of these distances valued at 0 at the origin and over 1 over n, rescaled by square root of n. So this converges just by the classical central limit theorem to a Gaussian. What do we see over here? Here we see the Hessians, here taken as a random sequence, of which we assume they converge to the population Hessian. And here is square root of n times the sample mean, and the population mean was 0. So we get all of at once, we get the central limit theorem. So here's my Hessian, and if this is a full rank, I can invert this and multiply this in there. Yes, that was assumption 4. So assumption 2, recall, told us that almost surely the distance function is twice differentiable if I have points close to the mean and the x, the random variable, all on the manifold. Well, this was a bit annoying. When is that the case? Well, this is actually the case if you consider the cut locus of the Fréchet mean, and if there's a neighborhood of the cut locus of the Fréchet mean, if this doesn't carry any mass, then we have twice differentiability of the distance function. So that's a theorem by Bhattacharya and Liege and Lin. But looking a little closer, so Wilderich, myself, and specifically Benjamin and Fernando, we look closer at this, and this is only the case if the manifold is compact. So if it's non-compact, you have to require slightly different. You have to require that you take a neighborhood of the mean, and then that the cut loci of all these points in the neighborhood carry no mass. But then it's still okay. So this deals with assumption 2. But assumption 4 was this convergence of the Hessian, which which in general does not hold. So this was discovered by Benjamin Elsner, 2022, this phenomenon of geometric smeariness.
Just real quick, remind us which one assumption 4 is.
Yes, good. Okay. Assumption 4 is the convergence of these Hessians, so that's a random process, empirical process indexed at a random index converges to the population Hessian. And this may not be the case on higher dimensional spheres, and you still see smeariness, which means you have a slower rate than this one. Okay, what else? And there is a central limit theorem by Benjamin myself, which actually does without assumptions 2 and 4, but they're hid in other assumptions. Okay, and still many, almost, so all, I guess, non-parametric methods in statistics require that we have, we have a manifold data with the mean, then we map everything to a local chart. So we have vectors, we want to do statistics with those vectors, and we want that this guy is twice differentiable, almost surely. And a typical chart is the inverse Riemann exponential, the log map. Okay, maybe here's a picture why things are so bad. So here's the circle. If we assume there's a random variable that has a mean at the North Pole, here the cut locus, the antipode is minus mu, and the log and the exponential chart are very simple. You just unwrap, cut it open. For this reason, it's called the cut locus. So you cut it open, and then the distance function just looks like this square distance function. And as we see, if we approach the cut locus, which is pi or minus pi, we have this kink here. So we have first derivatives, which are not continuous, and second derivatives only exist in the distributional sense. So this is really bad with terms of second derivatives. And it's even worse for the torus than a lot. So the cut locus has codimension 1. Here's a torus. If my mu sits here, the mean, then I have to cut open along these two lines. And okay, so now I guess it's time for precise definitions. So what's the exponential map? I guess most of you know. For the people who do not know, there's always so we are in a Riemanian manifold. There's a tangent space. Inside the tangent space is the tangent sphere, because we have a Riemanian metric. So these are the vectors that have norm 1. And then we consider curves that start at a point and have initial direction somewhere in a point in the tangent sphere, a direction. And GD6 are defined, or well defined, by the initial conditions. And the exponential is just another way of writing the GD6, the unit speed GD6. That's the exponential. So in general, this might only be defined on a small interval, but we're on a complete manifold, then it's defined actually for all of R. Okay, and we say such a curve, the geodesic is, or this curve is length minimizing if the distance from this point we started to the point after time t is precisely t. So unit speed is your geodesic, then we call it length minimizing. And recall, if we're on the circle, we start from the North Pole all the way down, we're length minimizing until we hit the South Pole. Once we're beyond, we're no longer length minimizing because it's faster, or it's closer from the other side. So in general, this means in every direction we go, there might be a t, a sup t, until which it is length minimizing and not beyond. If we're in a Euclidean space, this is infinite. They're always length minimizing, just straight lines. But on the circle, there is this TP in every direction, or in the sphere in every direction. This is pi. And the cut locus now is just the union of all those directions, or the going all over those directions, the points where we cease to be length minimizing. Of course, this might be void. And the cut locus can actually be decomposed in two parts. One is where we can actually, like on the sphere, if we go from the North Pole to the South Pole, we can reach it with several GD6. Or there might also be points which can only be reached by one unique GD6. So here's a nice example. If we do not consider spheres, but an ellipsoid, we're sitting somewhere on the top. That's our mean. That is here, this symmetry point. Then the cut locus is some interval, is some arc on the other side. So usually there are two GD6 from this side or from the other side reaching this point, but at the endpoints, there's only one GD6. So that is so this inside of this arc is the C plus cut locus, where we have two GD6, and the endpoints are the C minus cut locus. And it actually turns out, recall our overall assumption, complete and connected m-dimensional manifold, that theorem by Bishop, that the closure of these C plus cut locus is the entire cut locus. So what is known about the cut locus? It has Riemanian volume 0. It's actually a stratified space, which is at most of codimension 1. The exponential is a diffeomorphism outside of this. And in particular, then also our distance function is also C infinity outside the cut locus. So if this dot here is outside the cut locus of P. And there's the theorem by Huling-Ley and Dennis Barden, which I also talked about at the last ISAC, no, at the last, what was it? ISAC. It was ISAC, yes, of course, I'm getting confused. At ISAC 2. So their theorem says if the cut locus, if the C minus part is 0, so all GD6, all points in the cut locus can be reached by 2 GD6, then it carries 0 measure if we assume X has at most countably many point masses down here. And at the last ISAC, I formulate this as a conjecture, and then later on I talked to, whether this holds in general, I talked to Alexander, and I guess a month later or 2 months later, he sent me an email. I guess I have a proof, he said. And we worked on this proof, so make it digestible. I hope I will now present it to you, the digestible proof. So here's the general theorem that no matter in which situation we are, the cut locus can never carry any mass. So the corollary is that if you want statistics, indeed, this exponential or the log map is almost surely well-defined, and so is the square. So yes, we can do statistics without bothering about this. And we'll also see corollary is that the Fréchet function is differentiable at mu, has a vanishing differential. So it's really like a minimum. And as we'll see, the corollary is there can be no stickiness to unique mean on a complete Riemanian connected manifold, which was also in conjecture still a year ago at ISAC 2. Okay, now I will just, before I define the Riemann exponential for convenience only for unit length vectors, now I'll just define it as usual for all tangent vectors. Okay, then I guess I shall. So now we start with our so-called first order considerations, and we have to talk about semi-concavity. So a function mapping from the manifold to the reals is called B semi-concave if I take just any vector in the tangent space, I proceed along my geodesic, and I subtract, well, just as far as I go. So this length is t absolute value of v. So I square this. For convenience, I divide by 2 times b. If this is a concave function. So if I can make it concave by subtracting something of the order of t square.
Dumb question, Stephan, but which one is concave? Is this one concave?
Yes. So this is convex, and this is concave.
So you're subtracting something that looks like this.
Exactly.
So it's actually making it now bend downward.
Yes, exactly. Thank you. I appreciate all these comments. And we say it's locally semi-concave, and this can be done in a neighborhood for some b. And that's actually what we're interested in, locally semi-concave. So just some basic results. If I have a twice differentiable function, then of course it's locally semi-concave. I'll just take its Hessian and in the upper bound of its eigenvalues, subtract this, and then I'm locally semi-concave. It's even locally Lipschitz. We might also need this. Well, if my function is B concave, then it's also B prime concave if B prime is larger. Just subtract more. And this is a very nice property. If I have a locally semi-concave function, I can do directional derivatives. So I can start at my P in some direction V and take this derivative, this directional derivative. Why? Because, of course, here's my concave function. which has a directional derivative. So it's just the derivative here at the origin of this guy. And the derivative is, so directional derivative is also concave in the tangent space and locally Lipschitz if f was so. It's also easy to see. And now here's something very important relating to Ezra's comment. So if I have a local minimizer of a locally semi-concave function, so it should be kind of looking like this, which means the directional derivatives have all to be non-negative, then because it's a locally semi-concave function, it actually has to be, the derivative has to be flat, linear, and equal to 0. Okay, so these are basic ingredients. And now let's apply this to the Fréchet function. So here is the first lemma. We take a point Q, we take a small disk around it, and then we consider the families of the distance function index in X. So X can be anywhere on the manifold. And we consider those functions only in this little disk, this ball. And then the assertion is it's actually locally semi-concave with this constant, which depends on the X and the Q. And some constant which just depends on Q. The next is if we take the Fréchet function. So once we have this, we can just integrate this. This is non-negative, so we can integrate this. So the Fréchet function itself is then concave in this little neighborhood, as we here integrate over those guys. And we can also take the directional derivatives. They nicely pull into under the integral sign. Everything is non-negative, so that works. And this is more involved, that the Fréchet function itself has a linear derivative. So it doesn't have a kink, it's a linear derivative at Q if, well, the integrand is, that we see here, is linear almost surely. And we'll go through the proof. So for the first part, we use our distance function are actually non-negative. They're locally biconcave Lipschitz and bounded in a local, in a ball, say they are. Then f squared is also concave with twice SB plus L squared. This is very simple, straightforward to see that. And then we proceed in disk and annuli around Q to eventually get it for all x's. So this is more technical, but this is the critical ingredient. Now the second part, as I said, just integrating over non-negative functions and pulling the derivative in is straightforward. But what is not, it is also straightforward. If these guys are linear almost surely, then this guy is linear almost surely. Which is not straightforward is the other direction. Again, use a trick. So we now assume the Fréchet function has a linear derivative, which means if it has a linear derivative, the symmetrized version for any v will be 0. The symmetrized version is just taking the derivative at v and the direction derivative at the opposed direction. So if it's linear, then this should be 0. We'll plug this in. So we have the symmetrized derivative here. Well, it turns out if I have a function which is concave, then it is still concave if I change the sign here. Just go to the other side. So here's a concave function. And I take, so this is kind of mean, so I plug in the center point. It's concave, so it should be less. Well, if I plug in 0 at any of these directional derivatives, I still have 0, so 0 equal to 0. These guys, this integral has to vanish. And I picked, at this point, I just picked one single v. So almost there's a set AV on which this is almost surely 0. It has measure 1. So next trick is then we just take a dense subset of vectors. For each of these, I get a set where it's almost surely, this directional derivative is almost surely 0. The intersection of those sets still has measure 1. And then I recall that these derivatives are concave functions, so they're continues. So I have indeed the symmetrized derivative is 0 almost surely, which means these guys are linear. Okay, so this is our lemma 1, and with this lemma, we can do the first part, that the C plus cut locus cannot carry any mass in general, not only for point masses. So here's the first corollary tells us, so F is direction differentiable, actually at any point. Why? Because it's locally semi-concave, as we've just seen in lemma 1. And here at number 3. And we have, so this exists, we've seen this is 0 because we have a minimizer if we're at the Fréchet mean. So that is our corollary. And let's see. And now, what happens if I am at a point? So here's x, and the q is in the cut locus, plus. This means there are two GD6. Now, what is the derivative here of our squared distance function? It's actually the derivative of this. Here it is. It's square root of this one. So it's easy to see this is actually the inner product of a vector connecting the GDC connected to x, and here I'm at q. I start in direction v, here in direction v. So it's the inner product. And if there are several ones, I'll take the smaller one. And here this is parametrized in a way actually that the v points away. So I take the negative. Then I have to multiply with a minus sign. And here I take the minimum. So now it's the supremum. That's a result which is already in Lee and Barden's paper. I think that is it's also these days it's an exercise in differential geometry books. Okay, so we have this guy is not linear if and only if I'm in the plus cut locus, and q in the cut locus of x is the same as x in the cut locus of q. So this gives us if this is not linear, if the probability that these guys are not linear, the probability x in the cut locus is, then my f would not be linear, but we know it's linear because it's a minimizer, so that can't be. So that is the first part. Okay, let me now digress into stickiness. Why is this related to stickiness? So in stickiness, people, in phylogenetics, let's do phylogenetics, people are interested in, say, a couple of taxa, species, or whatever, or all of us here. We could be 1, 2, and so on. And one might be interested, what is our phylogenetic descendants? How about our ancestors? What's the topology? What's our common ancestor? So that would be a root. And essentially, Biller, Holmes, and Volkmann actually were the first ones to introduce a setting for phylogenetic trees. So we might do this descendants, come up with a phylogenetic tree with gene number 1 for all of us. Then we might do it with another gene, we get a different tree. And a couple of genes, what is the true tree? So it should be some average tree of all those. So we need some space in which we can do averages for Fréchet means, and that can be done in this BHV space. So essentially, this is as of the following. You're only interested in internal edges because there are always pendant edges to this taxa and to the root. So if in the simplest case, if we have just 3 taxa, an internal edge is actually determined by splitting the leaves and the roots. So here's 0, 2 on one side and 1, 3 on that side. So that's one axis. For this one, we have 0 and 1 on one side and 2, 3 on the other side. There are actually 2 trees. This has length 1, this has length 2. And yet here's a third topology, which is on that axis. And the central point in the middle has this is the origin, which has no internal edges. And in principle, the higher dimensional BHV spaces also look like this. They're way more complicated. They're stratified spaces, so manifolds glued together along lower dimensional manifolds. So let us just think of this space. So this is just a tripod. It's 3 lines, and we have put 3 trees on it. So you have distance 1, and we wonder about the mean, the Fréchet mean. Well, it's the mean tree. In that case, just sits at the origin by symmetry. What happens if I wiggle those trees? What happens if I move this tree a little up? Yes, I usually ask this question to the audience. So Everyone who's not seen this, what do you think? What happens to the point? Because we all thought when we, Ezra, Steve, and I guess a couple of, I guess nobody else is here at that group. At the SAMC some 15 years ago.
10 people there, but I think only 3 of them are in this room.
Yeah. So of course we thought this might move up. Thomas Hotz then did the very simple calculation. No, it stays here because if you move up a little bit, you say pull up with 1 plus epsilon. These guys still pull with 2 down. They keep it there. So you have to go all the way up to 2 before this starts moving. This was called stickiness. And there are various versions. So one, I think that's statistically most important, is sample stickiness. So we say a random variable sticks to a subset of, now for a moment, we're in a metric space, a general metric space, like the one before. If I take sample means, and the sample means are in this singular set after a random but finite random number. So samples don't move anymore. The end of statistics or the end of asymptotic statistics, no fluctuation anymore. And this is the case with this example that I showed. There are other flavors like perturbation. Like as I showed, we could pull a little up. We could place another point there. So there are various notions of stickiness. There's also topological stickiness. You have a neighborhood of, in a space of measures, say a Wasserstein topology or a total variation topology. And there's also, what is of interest for us is if we have a cat-kappa space, there are once again directional derivatives, and this is called directional stickiness if all directional derivatives are positive at the mean. And there's a theorem by Lars Lammers and others. If we have a unique mean on a connected complete Riemanian manifold, then all sticky flavors sticking to U are equivalent. And we've just seen this cannot happen on a Riemanian manifold. This is equal to 0. So there cannot be any directional stickiness and there cannot be any stickiness. But only to unique mean. Still open whether if the means are more complicated, think of a sphere, 1 point mass on the North Pole, 1 point mass on the South Pole. Then it's easy to compute that the Fréchet mean is the equator. So we don't know whether, we believe there's no stickiness even to the equator, but this is still open. Yes, there's no stickiness to lower dimensional space on Riemannian manifolds. That's a conjecture.
Sample stickiness is because the manifold curvature has data distribution or both.
Yes, it has something to do with curvature. As we'll see at the last slide, we'll see it has something to do with unbound negative curvature. Okay, now I guess we'll, okay, enough answer? Now let's do the second order considerations. So here we have a concept of Laplacians. So we define Laplacians of functions that might not be differentiable. We say the Laplacian, a point of a function is less or equal to C in the barrier sense, ET/BS, if there is an open ball around my Q, a twice differentiable function, which is larger than F on the ball with equality at Q, which is, well, this has a Laplacian, and the Laplacian of this one is less than C. So it's a little bit like our B concavity. And we say a function satisfies that the Laplacian, it's bounded in the barrier sense by -infinity if I can make C as small as possible. This holds for any C. Again, it's quite easy to see if our function is twice differentiable, then it's easy to see that, for example, well, this is made such that HC minus F always has a local minimum at Q. So suppose so it's not possible that my function, which is twice differentiable, the boundary is the bound is -infinity, because if, well, this has a Laplacian, so if I have a C, because it's twice differentiable, it has a Laplacian. If C is less than that, here take comparison function. This has a local minimum, so this Laplacian exists and is non-negative, would be a contradiction that our comparison function would actually have a Laplacian below C. Also, if I have two functions which are bounded in the barrier sense by their Laplacian bounded by C1, say, and C2, then the sum is bounded by C1 and C2. Also elementary. Next is also important. If I have a function that is bounded by 0 from above in the barrier sense, then it can have no local minimum. For otherwise, this h not 0 would have a local minimum, and that's a contradiction to, well, because that's a twice differential function, so it should be non-negative. And here's another important connection. If I have a b concave function, then I can, if I take a c which is larger than b times, so recall that essentially these are is the largest eigenvalue of a Laplacian, if it had a Laplacian, times the dimension, that's how many eigenvalues I have, or the dimension, then this is in general bounded by C in the barrier sense. Also, this is not very difficult to show. And here is the theorem we rely on. So Huling-Ley and Dennis Barden didn't have this yet. There's a theorem by Générau which tells us that the distance function is minus infinity in the barrier sense if and only if x is the cut locus of Q. And this holds only for dimension greater 2. That's at least what they said, but of course it holds also for dimension 1. Either we're on the real line, then there are no cut loci, or we're the circle, and then it's clear that this one also holds. And by the way, the Huling-Ley and Dennis Barden theorem can be applied because on the circle, there can only be, the only mass that can be on the cut locus is a point mass. So that's covered by their theorem. Okay, so we can forget about this dimension equal to 2. This holds for all x's and q. Okay, now here's how we proceed. Again, we apply to the Fréchet function. So here's our lemma 2. If I have any measurable set which has positive probability, then, and I take here the Fréchet function, usually I integrate over all of m. Here I only integrate over a. So it's kind of a derived Fréchet function. So this satisfies that, or if my distance squareds are bounded and their Laplacians are bounded in the barrier sense by some cx, then I just integrate this and I get a bound for the Fréchet function. So why is that? Why does lemma 2 imply the theorem? So we start with number 3 of remarks 2. What was that? I can actually separate by two functions. So this function plus that function gives me the Fréchet function. So here I'm outside the cut locus. Here take the cut locus. So I can add those two. By lemma 1, we've seen that the Fréchet function is locally semiconcave. In particular, this part, if I restrict it only to A, or to M set minus cut locus, it's still semiconcave. So then I have, I can, by 4, what was number 4 of remarks 2? It was, if I have something semiconcave, I multiply with a dimension. I take a C, which is larger than that, then this is bounded in the barrier sense by C. So there is some C by which it is bounded. This is important that we know this first part really does have can be bounded in the barrier sense. So this is not like, it's not plus infinity. So we have, it can be bounded. Could be minus infinity. This. Okay, and now we consider that part. Over here, the last part. So essentially, our lemma 2 says that in the barrier sense, I can consider those, I can just move the Laplacian inside, although this is not, so that's what I mean by this. If this guy is bounded in the barrier sense by some Cx, then this is as well bounded. So for this reason, I have these quotation marks here. Now, if the probability of the cut locus is positive, then this stuff here is bounded, can be made arbitrarily small, which means the entire thing, so this can be made arbitrarily small. It has minus infinity in the barrier sense. Here's something finite, so the whole thing is also minus infinity. That's what we see here by, yeah, that's the Générau theorem. But it has a local minimum, and remark 3, or number 3 of remarks 2 told us if a function in a locally semi-concave function has a minimum, then its Laplacian in the barrier sense cannot be minus infinity. So a contradiction, and the theorem is proven. So all we have to do, which takes a while actually, and I guess time-wise I will sketch the rest of the proof, we have to show lemma 2. Here we say lemma 2 follows if I'm able, so this was an arbitrary set, if I can decompose it into a countable sum and of disjoint measurable sets, and if I can prove this on every set, on every these sets. So why is that sufficient? So why does lemma 2 follow from this property? Well, now I'm just dropping in the barrier sense, because everything will be just Laplacians in the barrier sense. So I have at least one of these sets has positive measure, because the whole entire set has positive probability. So if this is the case for one of those sets, positive probability, I can actually squeeze in some epsilon, even 3 epsilon, you can squeeze in between the two. And now I define an increasing, so I just take the union of those sets. This is increasing up to A. And here is the rest, so the complement with an A, this converges to the empty set. The rest of those guys. Okay, now take a K, which is larger than I naught. I naught was the one set that has, at least one set has positive probability. So I take the Laplacians here over this union. This is a finite union. So I can do remark 2, which told me finite sums, the Laplacian can be pulled inside. So I pull it inside. This is a finite sum, and here's still my 3 epsilon from the one that has positive probability. So this, I get this bound. Now what about the rest? Yeah, so this is the rest. Here's the AK, and the rest is those BKs. So this is the Fréchet function, as we know. Even also these integrating over less is semi-concave. So here's my semi-concavity constant, sum bx, which we had in lemma 1, times the dimension. And I can make this a little larger than this is below that. So for some epsilon. Okay, now I consider this integral over the rest. Well, as these sets tend to the empty set, eventually this will be arbitrarily small, and this one as well. So I can bound this by epsilon. So putting things together, here's my sum, which I can decompose. There are just 2 functions. So the first one was bounded by this minus 3 epsilon. This is this guy. And the second one, well, I'll just plug in, instead of this one, I'll plug in that one. And the error I'm making is 1 epsilon here. Here's another epsilon. So it's 2 epsilons. And indeed, I get my assertion. Yes, okay. Then I shall probably sketch the rest. So we have the next step, we'll exclude that one of the AIs is actually C plus infinity, or that the Fréchet derivative is nonlinear. So I'll just go over this. It's just a little tricky. All those tricks are due to Alexander. And the other is, we can now assume for the rest that actually this derivative is linear. Do another couple of tricks. We'll just go over. And okay, so eventually then showing everything. Which brings me now to the last part to the discussion thus far. So you might recall lemma 1 told us that the Fréchet function is B concave. This is valid in a much more general context. So you can plug in anything That's be concave and integrate over this. Lemma 2, the same bounding in the barrier sense, is also valid, more general than just plug in Fréchet functions or distance functions. And there was a restriction that I required existence of second moments, but there is Sturm's observation that if you consider the Fréchet difference, so fix a cube, consider the difference of the Fréchet functions, then the squared parts cancel and you only have something linear that remains. So of course it suffices to do all this even if only first moments exist, like the classical strong law. So all results go through in that case as well, but it's a hell of a writing down things. So I didn't do this. And notably, I separately showed something which is a little more than Hughling's result, that the plus cut locus does not carry mass with our first order considerations. As you've seen, well, I skipped over the proof. This follows from the second order considerations as well. But for the following, this is important because people are also interested in general p means. So here we had p equal to 2 squared Fréchet, but of course people are also interested in Fréchet medians, p is equal to 1 or others. So if p is larger than 2, all proofs go through almost verbatim. Just replace 2 by p, everything remains nicely differentiable. What happens if we're between 1 and 2? Well, this is more complicated. And currently our second order considerations do not go through. But the first order considerations go through. So we get the Ley and Barden result now also for arbitrary masses on C+. And what else? P equal 1 is very special. There is an example, even on the circle given by Hughling and then it's Barden, that you have the mean is on the North Pole. The South Pole still carries mass if, for a suitable example, if and the North Pole also, so the mean also carries mass. But if you require that the mean does not carry mass, so this one is an additional condition, then the first order considerations also go through. In that case, the antipode cannot, or the cut locus cannot carry mass. Now further extensions, yes. So even, as I said, for the Fréchet means, whether the other part of the cut locus carries no mass is still open for arbitrary Fréchet means p between 1 and 2. So there's still something open. And what about if the manifold is not complete? Well, if the manifold is non-complete, I guess, yes. So you still define the plus cut locus that the derivative is of the squared Fréchet, of the squared distance is not linear. And we can still show this has 0 probability, but the rest, the closure can be very complicated. I'm not too familiar with this. There are some papers on this. And we believe that you need additional assumptions, like in case p equal 1, to have that this part of the cut locus also carries no mass. Now, finally, this is Gigang's question. It can be shown that the derivative of the Fréchet function at the Fréchet mean is linear, is equal to 0, also for Alexander spaces with curvature bounded from below, which is not the case in BHV spaces. Curvature is arbitrarily low at these singularities. So this rules out under additional assumptions, one being, for example, as I recall correctly, locally compact, all sticky flavors at a unique mean. Again, it's open what happens in non-unique means. And naively thinking that the Fréchet function is differentiable at the mean, is the Fréchet function always differentiable? Well, it can be. So Fernando Gallarz-Garcia and co-author Guajaro came up with an example that every point, or so if I'm in a compact manifold, then all cut loci, even the C plus cut locus reaching with 2 GD6 is not empty for any cube. And with this, you can easily construct Fréchet functions which have non-linear derivatives at a dense set. but not at the mean. Okay, and recall the conjecture even that we don't know whether there's stickiness at non-unique means on complete Riemannian manifolds. Okay, for all this and further details, see our paper, which is in the archive from this year. Thank you very much.